Firstly, thank you, Sarah, for kind introduction. And I have to say that this is, I think, the third or fourth time I'm here at the UofT Coders seminar. First time on this side of the table. This is the first time I'm giving a talk. And thanks also for this opportunity to be here. I have to say that from my experience, I was always amazed how wide variety of people came here. And now when I was preparing my lecture, that amaze turned into a kind of like a fear, because I wasn't really sure what level of advancements should I prepare or would be of interest for you. So this is a sort of a disclaimer right from the beginning. So if you will find this to be too trivial, I apologize. And as for compensation, I encourage you to email me later on if you have any questions. On the other hand, if you may find it too advanced, I also apologize, and the same applies. Just contact me. I'll try to elucidate the things later on for you. So this is the disclaimer. Second thing would be probably I think, or I feel that I should motivate this talk. So like, you know, if you are about to spend 60 plus 90 maybe minutes here, it would be good to know why it's a good thing to deal with measures of association and testing some hypotheses that can be derived from that. So the way I see things, in the very fundamentals of science, or the testing where the two things are associated is the most fundamental part of science. No matter from what field you come from, I'm sure that sooner or later, or maybe in the previous past you already did, try to assess whether something is dependent on something else, or some things come together or are affected by some common factor. For those of you who are more, from what I heard, interested in machine learning maybe, well, in the very core of pretty much any machine learning algorithm is some sort of measurement of association between features in that case. So measuring association between things is probably very important in any science. Now, when I say measure of association, in fact, I mean three things at once. First, I mean being able to visualize things or come with some visual assessment of two maybe associated things. Second, I mean effect size. So we always, when we say that we measure association between something and something, we want to know how strong this association is. And the third aspect is to assess its statistical significance. That is, to test whether such a strength of association as measured on the given data set could come just by coincidence. So the third of these is typically measured by something that in statistics is called p-value. And to give you a bit more, a bit better imagination of what I mean, I'll start with something that I call Martini Experiment. So Martini Experiment, I hope that you heard about James Bond. So James Bond is, among other things, he's known for his taste in martini that are not stirred but shaken. So imagine the situation that you will have a James Bond here, and you will give him, I said, 16 trials. So he will have 16 samples of martini, and some of them would be stirred and some of them were shaken prior to his trial, and he would have to guess. And let's say he will have 11 correct guesses. Now, question is this by chance, or really Bond is skilled in tasting martini and he can really distinguish shaken or stirred? So I'm gonna toggle to sitting mode, and I'll try model this in Python. Before I'll do that, I would like to spark a little bit of like let's think about it together. So if James Bond will be really just a poser and he really doesn't know anything about martini, and even less he knows about how to distinguish shaken and stirred martini, we could model his ability to guess with random process. Does it make sense to all of you? So I could come up with coin. I said here 16 trials. So I will throw coin 16 times, and then I will measure how many times it fell on head on one of the sides. And I would have one statistical sample saying it fell 5 times on one side and remaining 11 times on another, or something like that. That means I will have one sample only. The statistics on sample is nothing. So what I would probably do, I would pass the coin to one of you. You would throw it 16 times, and you would always write down how many times it fell on one side. And you pass it further and further and further. Well, obvious disadvantage, it will take a lot of time. We will have to repeat it probably 1,000 times to get statistically rational or sufficient amount of data. Good thing is that we don't have to do it using coin. We don't have to do it in some mechanistic fashion. We can simulate it in computer. So now I'm really sitting and try to code. This is the second disclaimer, because this is the first time I'm coding in front of so many people on Earth. I hope I will be okay. So first we import some libraries. NumPy. We always start with NumPy in Python. From SciPy, we will need only module stats. We will need pandas. And we will also need seaborn. So these are the libraries we will use, and I promise that throughout the whole lecture we won't use anything except of these 4.
Can you make it just a little bit bigger?
Sure, or at least I can try. Should I speak louder? Okay, I will speak a little bit louder. Oh, I said number of trials we gave to Mr. Bond is 16. I'll stick with the number. Was 11. And probability of success is, in this case, 0.5. One thing I would like to note, some of you may think, okay, maybe it depends on how many of these 16 samples were stirred and shaken. Not true. It doesn't matter. This is the probability in any given trial to be successful just by chance. I hope you can you feel the difference. So yeah, and I said we do a simulation. So the simulation in this case will be done using so I said that canonical experiment will be using coin, and I said that we can simulate it in computer. So NumPy has a module called random, and in a random module you have a lot of functions that can generate data from certain distribution. In this case, I'm going to use distribution that is called binomial distribution. I won't talk much about binomial distribution in theory, because after all, this is supposed to be especially about Python, so I will stick with coding part. First thing, the binomial distribution will require us to input is the number of trials, probability of success in one trial, and number of samples we would like to generate. And don't hesitate to be bold, ask for 100,000 samples, even a million should be okay, and let's run it. So I'm going to show you.
What is the size? 10 to the power of 5?
It's 100,000 in this case, 10 to the power of 5. Yeah. This is the distribution of the success rate. I don't know how about you, but I really don't like this blue line there. So most often what happens if I have a 16 trials, no surprise, half of them will fall on one side of the coin, and another half will. So if I would throw a coin 16 times, not much of a surprise, and most often what's going to happen is it's going to fall 6 times on one side, 8 times on one side, 8 times on another, and evens where when out of 16 trials we would have a hat 15 times are relatively rare, which we can see here. So when I said that we are testing some hypotheses, in this case, what we are doing, we are trying to find out like how often does it happen just by chance that coin will fall 11 or more times on one side out of 16 attempts or 16 throws. Because this actually answers the question, what is the chance that James Bond was simply lucky and he had 11 lucky guesses? So to answer that question, we can do following thing. We can simply say how many times simulation was greater or equal to number of So this is simply, we are asking how many times, just by chance, coin would fall on one side more than 11 times or at least 11 times. I believe the more elegant way and more Pythonic way how to show this is, or how to calculate this is following way. So what I just did is I ask whether value in the tuple called simulation is greater or equal to number of successes, in this case 11, which would eventually return just Boolean tuple. And mean of the Boolean tuple is basically relative number of truths as a fraction of total number of elements. Does this make sense to you? I hope it does. Okay. This is quite Pythonic way how to do this. So what does it tell us, this number? It tells us that there is approximately 10.5% chance of getting 11 or more successes, 11 or more times one side of the coin, head of the coin, in 16 trials, which with respect to our Martini experiment means that there is a 10.5 roughly % chance that James Bond was simply lucky, and in fact he doesn't know much about Martini. Is 10.5% chance something that convinces you? Who is convinced by knowing that James Bond could be lucky, could get that success just with 10% chance? Well, typically statisticians or in a science, we require, this is p-value. Without telling you, this is the p-value. We require p-value to be lower than that. And now don't get confused, lower doesn't mean worse, it means better. So we want chance that some event happen, or probability that some phenomena occurred by chance, typically below 0.05, that means 5% chance, or 0.01, that means 1% chance. One last way, or one last thing regarding this Martini experiment that I would like to show you is how, because this is still quite laborious way how to do things. Another way would be to take the, I'm sorry, here and there I have to help myself with my notes. Reach to the stats package and ask directly for executing the binomial test. what I just did here, I used stats package to execute binomial test. That means it tests exactly the same thing that you just tested before, which means how likely it is that out of the 16 trials where one outcome can happen with 50% chance, I will have 11 outcomes alike. And for those of you who may be interested by what's here, this alternative equals to greater, it means that we are testing the hypothesis that event can happen with equal number of successes or greater. That means 11 or more. Someone could actually ask for opposite thing, like less than something. So this part was to give you some imagination on what is p-value or what is statistical significance. Now let's get to the actual measures of association. I want to tell you that when we are measuring associations between variables, what matters the most of everything is what kind of variables we have. So it's probably something different to measure association between two numeric variables that are numbers like height and weight or something like that, and measuring association between numeric variable and categorical variable. Do you know what categorical variable is? Can you give me some examples of categorical variables?
Cities or yes or no?
Yeah, exactly. Gender, ethnicity, or degree of education, and so on. True. And so I mentioned association between two numerical variables, association between numerical and categorical variable, and well, quite naturally, there is a third option, measuring association between two categorical variables. I kind of intentionally avoid option that there can be ordinal variables, so the categorical variables where levels or unit values can be somehow ordered. And quite honestly, I won't cover this topic today, or at least I'm not planning to. But I'm very much willing to provide you any guidance on that in case you want, like afterwards. So if we are trying to measure association between two numerical variables, most often is not the only way, but most often we are talking about correlation. I bet you heard the word correlation, every single one of you. Have you? Yeah. Well, correlation is the term that is used quite frequently, not only in technical language or scientific language, but also in a common language. Kind of the problem is that different scientists or different fields of science may mean quite different things when they say correlation. So in plain language, something correlates with something, it just says that there is probably some association between two things. When it comes to any mathematics or any quantitative science, when we say correlation, we probably mean very particular way how to associate two variables, and the word correlation itself is most often not enough because we know multiple correlation measures. So I don't want to go into theory of things. I'd rather give you a few examples, and on these examples I will also, at this point, I will tell you which kind or which type of correlation to use in which case. So, not that I'm some sort of annotation freak, or maybe I am, but I'll make a note here that this is about correlation. So, and at this point, I would like to load the data set I'm going to use, which is MPG dataset. Now, right away, I'll show you a sample of this data. So, MPG dataset is a dataset that stores information about models of cars. It has information about the mileage per gallon. To be honest, I don't know much about cars, and but what I know is, and also I'm from Europe, obviously, and we don't measure the efficiency of the car in miles per gallon, rather like amount of liters of gasoline needed to make 100 kilometers. But I assume that I think that MPG, the lower it is, the more efficient the car. No, actually higher it is, the more efficient the car. Okay, higher it is. So this is the miles per gallon cylinders. I assume it's a number of cylinders in the actual engine of the car. Displacement would be probably the volume of some of the volume of the individual cylinders. Horsepower is quite obvious, is the power of the engine. Weight is the weight of the car. Acceleration is the ability to accelerate. The year when the model was introduced and the name of the model. So first thing, before our proceed is, I'm going to get rid of lines that contain missing values. And this is simply to simplify things, so we don't have to tackle with this down the road. I know that in practice, you usually don't want to waste data like that, but in this case, we won't hesitate to do that. I'll start with probably the simplest thing. So when someone says a correlation and that someone is scientist, without saying anything else, probably they mean Spearman Pearson correlation coefficient. So now, what do you think? I'll focus your attention on mileage, so the miles per gallon. Which one of these will be probably the most correlated with mileage?
Acceleration.
Pardon me?
Horsepower.
Weight.
So that is something that we could probably test right away, but let's keep it for later. For now, I'll authoritatively tell you that I want to test horsepower simply because I prepared myself for that. Now, you don't know the result yet. Note that I expect two outputs. The first is the R, which is effect size. The second is p-value. So before I'm going to show you these numbers, I want to tell you that first says simply how strong is the association as measured on the given data set. Second measures how likely it is that the same effect size would be observed simply by chance. One without another doesn't have much of the meaning. If someone, or it has a meaning, but it's not sufficient. If someone will tell you that we have a significant association, it's nice, but if it is very weak and the significance was achieved, and this is quite possible, simply because the sample size was huge, it's okay, but there is still weak association. On the other hand, if we observe strong association, there is still an option that it is simply by chance. So I'll print the RNP. So we see that it's negatively associated. The correlation is negative. That means that with increase of the horsepower, we have a decrease of mileage. So more powerful car we have, less miles per gallon it can make. That means more gallon it requires to make same journey. And this number, notice how low it is. It's very low, like very close to zero, right? So it tells us that this is certainly not, or almost certainly not the product of chance. Does it make sense? I hope it does. All right. So we have an effect size, we have a p-value, but I told you that there is this third aspect. When it comes to measures of association, it is very much desired to do some sort of visualization or to do some visual inspection. So in this case,
If you have a Python tree, that print should be in parentheses. If you're getting you're getting parentheses. The print.
All right, so we got this plot that clearly shows that as the power of the car increases, the mileage is decreasing. Well, here is a kind of a caveat. We used Pearson correlation coefficient. Pearson correlation coefficient measures linear association. Linear means that if one increased by 1 unit, another one would increase by 1 unit times some number, no matter where you start. Probably this is confusing, but if you don't mind, I will help myself with using Wikipedia. Note one thing, that whenever this is a line, whenever one variable depends on another, so that when we put the sketch report, we have a line, the Pearson correlation is equal to 1. Of course, there is some once the association becomes fuzzy, it drops and then 0. But look at this, for example. It's very clear that this, whatever would be on x-axis and y-axis, these things must be somehow associated. This can be just by chance, right? But Pearson shows 0. And same here, and same here. Well, that's the strange and also the weak side of the Pearson correlation coefficient, that it is focused or designed to assess linearity of the association. And if I go back to our plot, you can see that this is certainly not linear. Right? This is whatever this is not linear. So, is it a problem? Per se, we could live with that. However, there is one hidden thing that you may not realize, that this p-value didn't come like from heaven. This p-value has been calculated by the function we used, and that function, without telling you, assumes a lot of things about data you are sending. Among the assumption is that there is a linear association tested, it's A, and B, that the both variables we use for input are normally distributed. Are they? We didn't even check that. But we can. So, does it seem normally distributed to you? Do you know how normal distribution look like bell curve? So, maybe if I will really use all my imagination, I could force myself to believe this is normally distributed, but most likely it is not. And if I look at the horsepower, probably it will be similar. So using the using Pearson correlation coefficient wouldn't be that big problem, even if it is not linear. But obtaining a correct p-value using the ordinal function that assumes normality of the distribution would be a kind of like, it wouldn't be correct. simply because these variables are not normally distributed. In theory, you could instruct this function to, instead of assuming things and so on, just go hard way and do something that is simply some randomization test that would shuffle data and measure correlation, and we'll shuffle data again and measure correlation, and we'll do it a lot of times. But much more rigid, statistically rigid way of doing these things is reach for other measure of correlation, in this case, Spearman correlation coefficient.
What do you, in this situation, can we transform the data using a log?
In this given situation, or are you asking in general?
In general, yeah.
Well,
in this situation, in general.
In general, not always, and in this situation, my guess would be probably not. Even if I logarithmize this, I am not entirely sure if I would obtain something that is, maybe it would be close to normal, but I wouldn't be entirely sure. And also not sure if I would force this to be linear, maybe yes. But generally speaking, there are certainly scenarios where you won't achieve a linear relationship. So that's why it's probably wise and better to know wider collection of measures for correlation. So when we use Spearman, we obtain effect size that is slightly different, and also the p-value. Qualitatively, we still have the same result. We know that mileage and horsepower are negatively associated, yet the association is very significant. There is one thing I forgot to tell you when it comes to the effect size. Effect size, no matter what scenario we are dealing with, there are some properties we demand the effect size to have. One of these is supposed to be somehow, it should fall into a certain range. Correlations have this property. They are from -1 to 1. And I think that's the ultimate property we demand. We want effect size to be in a certain range. And why we want it? Because it allows us to compare things. We can measure association between this and horsepower, the mileage and horsepower, the mileage and something else. Well, if we use even slightly different methods, because these measures are in fact different, if we end up with numbers that are still in a certain scale, then we can tell something about the strength of the associations, even if different methodologies were used. I assume this may not be entirely clear to you at this moment, but I hope that I will clarify it later on. So we use Spearman, Pearson correlation, Spearman correlation coefficient. Do you know about some other correlation measures? There is one quite often used called the Kendall correlation. So, and another thing that I should have told is that while Pearson is measuring linearity, Spearman is measuring monotonicity. Do you know the difference? So imagine that I will take all the people in this class, including myself, and I would measure our height and weight. And I would assume there is some association between that. So if I would plot on x-axis our weight and on y-axis our height, well, linearity would be if they would be around some line. This is, I don't know how likely to happen. I don't know much about it. My imagination is probably not. But what is much more likely, they will be monotonous. So most often, like if you look at the data, if one grows, another one grows too. That's my ad hoc definition of monotonicity. So unlike Pearson, who is focused on measuring association between variables that are linearly associated, Spearman is focuses on measuring association that are monotonous. This is for what it is designed. Yeah.
As I understand it, both the variables increase together or decrease together. Are they supposed to be monotonous?
They can. So if one grows with another, it's always, so the whole span of values, we would say it's monotonically increasing. If it will be decreasing with another, so very unimaginable case that weight will decrease with height or vice versa, in this case, we had something that is imperfectly but monotonically decreasing, right? So we see there is some fuzziness, but overall, it's one declines with another. So this one is growing, this one is declining. So in contrast to these, because I already started with Kendall, and I think so. If the Kendall measures the relative number of pairs, so imagine that I will measure height and weight of every single one of us, and then I would measure how many times we have concordant pairs. So I'll take two persons, one is taller than another, one is taller than another, and this one is also heavier than another. This will be concordant couple. If I would have a scenario that one person is higher than another, yet lighter than another, this is disconcordant couple. Kendall correlation coefficient measures just the relative number of concordant to non-concordant couples across all the combination of couples in the set. Okay. So this will be Kendall. I'm not going to measure this one. Instead, I'm going to move to association between numeric and categorical variable. So probably the quick question, is it even possible? Can we measure association between numeric and categorical? Probably yes, we do it quite often, or if not we, probably someone else. I mean, statisticians or people in social sciences, I'm sure they measure very often, like dependence on of something IQ on level of education or something like that, right? It's or military rank or something like that. So yeah, it should be possible. Now, how to do that? So I wrote something here, ANOVA. ANOVA is a shortcut for analysis of variant, and it's one of the methods. And one of the methods that implies is not the only one, but it's very often used for exactly this task, measuring association between numeric variable and variable that is categorical. So if you look at our data, so what categorical variables we have here? We have origin, and that is certainly a categorical variable. We can take a look on so we have three types of origin: USA, Japan, and Europe in our data set, and it's almost like tempting to assess which cars have a better efficiencies. So, any bet? Okay, who bet Japan? Someone who would bet on Europe? Sure. Yeah, well, we don't have that level of granularity to say like which country. At least the So I said that one of the three aspects is visualization. I cannot help myself. Is here someone who would bet on United States as the producer of the most gas-efficient cars? Probably no one. So that was a good guess. Yeah, Japan is, or at least in this data set, seems that the cars manufactured in Japan have the greatest. So this is the visual inspection. It doesn't tell everything. We probably can tell already something about it, but it's not enough. We would like to know what's the effect size, and we would like to know what's the significance. So yeah, first thing I'll have to not sure what I just did. So basically, I created all the entries in the column miles per gallon into 3 categories. So all right. Once again, what I did is I took the column called miles per gallon, MPG, and I divided it into 3 groups. So I grouped it by, and I grouped it by origin. So this thing stores value, 3 tuples, each of them storing mileage from for cars of different origin. ANOVA in stats package is stored in a function f_one way, and it requires as many tuples to be on input as many tuples you have in your data set to test. And quite convenient way is to do it like this, and use asterisks to inform that it won't be like tuple, comma, tuple, it will come at once. So certainly very significant, very unlikely that such a differences would be obtained by chance. And this is what kind of effect size this is. This is F statistic. I'll tell you something about it, but first I would like to get back to, so what we are doing here. We say we are measuring association of mileage on origin, but that very same thing can be interpreted by, from other point of view, that we are trying to assess whether there are strong or even better significant differences between mileage from individual manufacturers, origins of countries of origin. In a sense, it's the same thing, like measuring association and checking whether there are differences between groups. So that's a notion that I consider important to mention. Now, F-score is not really an effect size. Why is not an effect size? Because effect size, as I said, we demand certain properties. We want it to be from some certain range. As you can see, this is certainly not from 0.1, it's not from -1 to 1, and I guarantee you it has like no limits. If I would just multiply the whole data set several times, then the number would probably change. But because this is not an effect size, we need to have some effect size. And in fact, there are so many various effect sizes. If you would search in Wikipedia for statistical effect size, I guarantee you may find maybe 100 of them. So I'm going to use, for for this particular task 1, and that one is called eta squared. And here on the board, there is a formula that says how eta squared can be calculated from F statistics. So here is the F statistic. And in this case, is the number of samples we have. So all the models we have in our data set, or the lines, if you will. And K is, you all say degree of freedom. I'm afraid that I'm going to get on a thin ice. But in this particular case, it means how many groups we have here. We have 3. So I'm going to define a function that will calculate the squared from F statistic. Well, I very much hope I have this right. So I think I have a error somewhere here. All right. So eta squared has a demanded property. It can only have values between 0 and 1. Now you may ask, okay, so 0.33, is it odd? Is it strong association? Is it, well, it's quite strong association, certainly. I cannot really tell you that yeah.
Can you just scroll up a bit?
Pardon me?
Can you just scroll up a bit?
Oh, sure. I cannot really tell you that everything about 0 point something, 0.3 is okay, and it's strong effect, and everything below is not strong. However, each field of science has their own standards or established thresholds for accepting something as sufficiently strong. But p-value is very much of help here, because it can tell you at least how likely it is that it can be obtained by chance. Now, there is one other caveat, and it is that ANOVA is also a function that has a lot of assumptions. And again, ANOVA assumes that the continuous variable, the numeric variable that we are testing, is normally distributed. And we already showed that it is not. So, okay, so Thomas, why are you showing us this if it doesn't work? Well, the reason is that I just want you to know that there is such a thing as ANOVA, but it's not the only way how to do things, and it's not the correct way in case that you have non-normally distributed variable. So another way how this can be done is using something that is called Kruskal-Wallis Test. that in contrast to ANOVA doesn't have any assumption about distribution of the numeric variable. In contrast to ANOVA, it doesn't give us F-score or F-statistic, it gives us H-statistic. So, oh man, again, statistic. Well, unfortunately, we have to go through the same torture as with the F-statistic. We have to convert it into a effect size, ideally the same as effect size, which is eta squared. So, there is another formula which is not on the board. But I can either write it there or I can write it here in the notebook. Maybe better to do it in a notebook. So n is again number of samples, and h is the H statistic. Pardon? Yeah. And I'm going to define the function that it will calculate eta squared using F statistic. Now I apologize, but here is a mistake. Okay. Yeah, I see. I very much hope, yeah, it's the same value. So I hope that now it starts to make sense. Like eta squared as effect size is the same regardless of what we used. In fact, it shouldn't be, because ANOVA assumes or effect size produced from ANOVA shouldn't be affected by the fact that it's not normal, but p-value may be. And yeah, so
The formula isn't H times n plus 1?
I think it's supposed, pardon me. I think, yeah, maybe. This is how it's supposed to be. I'm very sorry for that.
Can you just go back to how you type the formula?
You want to see the, this is, pardon me. Do you mind me continue? Is it okay? Okay. So, taken together, what we did is we did visual inspection of the data. We used two different methods. One of them is optimized for working with normal distributed variables. One is a bit more generalistic to calculate some statistics and associate the p-value. These statistics, however, are not directly interpretable as effect size, so we converted them into our effect size. In this case, I used eta squared. The fact is that eta squared is not only one of the many possible, it's only one of the many possible measures for assessing effect or assessing association between numerical and categorical variables. Probably if you visit any stat page or mathematical pages like Wolfram Mathworks or even Wikipedia will probably provide you with a lot of information about alternative measures. So this covers the second case where we were measuring association between numerical and categorical variable. Well, and I promise that I'll tell you something about also the third case where we have two categorical variables and we want to measure association between them. So there is one problem that this data set doesn't have that many categorical variables. In fact, we have only one. So what I'm going to do, I'm going to create another categorical variable. What I just did is I calculated the median of the weight of the cars in our data set. So in case you don't know what median is, it's just the value that half of the values are above and half are below. And I coined this car size. So I divided the cars into big ones and small ones. And so we are going to test, associate, or demonstrate how to measure association between categorical and categorical. So other categorical variable is the origin. So let's do that. Now, I said that one of the aspects of assessing association between variables should be some visual inspection. However, that doesn't have to necessarily be a plot. Sometimes, and this is this case, what is more convenient is simple table.
Can you put the previous code into a line?
Pardon me?
Previous code, line 79, can you put it in 2 lines?
Now, this is what I just did. I created what is called confusion matrix. And don't get yourself confused by its name. It's just the metric that stores frequency of occurrence certain conditions. So it says how many big cars in our data set are from Europe, how many small cars are from Europe, and so on and so on. I think just by very quick look, you can easily tell who's making big cars. And yeah, so there is strong bias towards big cars being produced from in US. One very intuitive, quite maybe hopefully intuitive question, like if there will be no association between origin and the size of the car, what values would we expect here? I mean, we don't have to get to precise numbers. It's just, is there a way how we could tell what is expected and what would be the expected values here? So let's think together. If we know that in the given data set, I'm going to fabricate the numbers. In the given data set, half of the cars in the given data set are from US, or US models. And half of the cars in the data set are big cars. Then if there will be no association, we would expect that number of big cars from US would be half times half, so approximately 1/4. So this is expected value. Now we know what we could in theory do. We could really calculate expected value for every single element of this matrix, and we can compare where we have more than expected, where we have less than expected, and it will tell us really a lot about the association between origin and size. Well, again, good thing we don't have to do it manually because there are tools that do it for us, and I'm going to use one of these. So the tool that can do this for us is in package stats. It's called chi-square contingency because it uses contingency metrics. I said confusion metrics, but at this given moment, I don't think there is much of a difference between them. I think like the contingency will be related to binary cases, and or vice versa. Well, anyway. I'm expecting 4 outputs. So one is the chi-square statistic. So again, it's just some statistic as F statistics or H statistics, which I think at this given moment, we are all allowed to think about as some abstract number. Accompanying p-value, degrees of freedom, which in this case is the number of either less of the number of columns or rows minus 1. I hope that I didn't say something that is not entirely correct. And expected table of expected values. I'll print kind statistics and associated p-value, and we can really see that there is very strong association between size and origin. And the problem is, as was before, that statistics is not really is not really effect size. And to get an effect size, or what would be the appropriate effect size here? So I'm not going to stretch it too much. So it's the same thing as with the eta squared. There are probably many of them, but the one that I believe is the most frequently used is the Cramer's V. And I'll show you how Cramer's V can be calculated from chi-square statistic. It's going to be, I'll start again with equation.
on the equation.
Pardon me?
Translate on the equation.
Should I?
How to write it.
I don't
Bring
know.
it on, bring the equation, bring the code.
Oh, pardon me. So, meanwhile, I'll just tell you what individual things mean. So, chi in this case is quite obvious. Is the output from, or is the chi-square statistic, and is the number of observations, and this is the number of rows, and this is the number, n is the number of rows in this table, and m is the number of columns. So, in fact, what could stand here instead of that form would be degrees of freedom, or DOF, which, as I said before, is the minimum of the number of rows minus 1 and number of columns minus 1.
So here is 1.
In this case, it's 1. Yeah.
The UOF in line 8 to be 2.
Once again.
If you print the UOF.
That's a good point. I think it should be actually max of these two. Yeah. All right. And yeah, the promised recipe to get Cramer. So this is the recipe of how to get Cramer's V from chi-square.
We don't have functions that are already written for the.
Well, yes and no. I mean, in the stats package, I don't think they are. However, if we would expand the pool of packages, then, for example, scikit-learn is something that I was planning to say at the very last, contains much wider collection. The reason I didn't use it is that I didn't want to go with like such a wide variety of packages, and also at the end, if I would use scikit-learn, it would be all reduced to a simple using functions that their meaning and their functionality is not entirely known. So. So this is the Cramer's V, and in fact, that is the end of my talk. Only one thing I wanted to say, but that was already said, that this is only one of the many possibilities on how to approach problematics of measures of association in Python. Besides that, there is quite a known package called scikit-learn that has also a wide variety of functions that can be used. Maybe actually even more straightforward, maybe, but on the other hand, maybe less educative. Then probably the last thing I should say is thank you for your attention, and I hope you enjoyed it.
Thank you.